All right. So I want to. One of our word problems that we're going to start with today is the movement of a Ferris wheel. Now, the movement of a Ferris wheel is periodic because the height, which could be considered the y value, the height repeats. Right? It's here, 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 it's here. And because a Ferris wheel rotates at the same rotational speed, this is periodic. Okay, so we're ignoring the fact that the Ferris wheel stops every so often. We're just thinking about the movement of a Ferris wheel. And so the graph that I have here is height versus time. Okay. So as time moves on, we go further into the x-axis. Okay, so let's press play. How do I do this? No, I don't know if there is a play button. Okay, I think I just do this. So the red square is your little compartment. Okay. Can I move it? No, I can't move it. So all I can do is I can move this along. Whoa, that was way too fast. How do I, sorry. I'm looking for a play button. I don't see it. All right. No. Okay, interesting. Can I change this? No. Okay. So at time equals 0, where are we? At the bottom. So even though the height of the Ferris wheel, so notice it's like not on the ground, it's a little bit higher. Okay, because of the cabin. So I'm going to try to go as slowly as I can. We are rotating. Can I move this down? Yes, I can. What direction are we rotating in? Counterclockwise. That doesn't actually matter. Because what is the y-axis? No, the y-axis is height. And the x-axis is what? So it doesn't matter. Does it matter whether we go clockwise or counterclockwise? No. But in the questions, you will have to think about that. So what has happened thus far is we started at the bottom. We're rotating. We reached the maximum height, and now we're coming down. Now, notice that this graph is not linear. It's not a straight line up and a straight line down. And notice that when you're in the cabin right at the bottom, and then you move to the next cabin, you actually, the height difference is not large. Versus when you are in the cabins here, you go from one cabin to another, the difference in height is much greater. Do you see that? And so that is why we get this curve in the sine curve, is because the height is increasing slowly here. Now, where does the height increase the fastest? On the sides here, right? Remember slope? So if you look at the slope at the specific point, like the slope here is low. It's like this because the height is not changing quickly. But the slope right in the middle is at its steepest because right here is the spot where the height changes most drastically. Okay? And then once again, when we get to the top, you can see that the difference in height between the cabins is quite small. So again, the slope gets smaller and smaller to the point that when you're at the top, does anyone know what the slope is right at the top? It is. Watch this. It's like this. Right at the top, your height for a split second stops changing because you have to change direction. That's sort of the physics explanation of the Ferris wheel. Now, when the Ferris wheel goes, so first of all, which curve are we kind of creating? Is it more a sine curve or a cosine curve?
Sine.
Really? Really? Did we start at the max or the min? We started at the min. I would argue that it's more of a cosine curve. Except that, what do you see there? A negative A value. It's reflected, right? A cosine curve usually starts at a max, but if you flip it upside down, then this is the cosine curve. If it was a sine curve, where would we be starting? At the central axis. Beautiful, right? The central axis is this area of the Ferris wheel. So sometimes questions say that the cabin, like the platform to onboard, is right in the middle, right? That would mean, oh, we're doing a sine curve. But if you're entering the Ferris wheel right at the bottom or right at the top, then we're mimicking more of a cosine curve, right? So if you flip this upside down, oh, that's the cosine curve. And if you go once around, how many cycles of the curve is it? One. And it makes sense. That's a period, right? One periodic behavior, one periodic cycle gives us one period. Whoa. So now I'm right at the bottom again, and I've done one complete curve. Okay, do we kind of see that? And so as I move on, the curve continues. Okay, same curve because the height never changes. This is the periodic behavior. Does this kind of make sense? And remember, the x-axis is your time, not your distance. The Ferris wheel is not moving. The Ferris wheel is in its place. The only thing that's changing is time. So as time goes on, your height changes appropriately. Got it? Okay. So let's move to page 10. Let's talk about certain types of real-world applications that model periodic behavior. And from physics, I know I keep bringing up physics, but physics does include a lot of functions, especially sine curves, right? Where do we see sine curves when we talk about, like, in physics? What type of waves? Yeah, waves. What type of waves? Pardon? Yes. And, like, which unit did you see waves come in? In the waves unit? Waves and sound, right? Sound waves are sinusoidal, right? So when you're listening to me, that is because there is a sine wave entering your ear, right? It's kind of cool. When you look at the waves in water, as long as there's no disturbance, you are seeing a sinusoidal wave. So waves occur in nature. What's kind of cool is, you know, when there's like a crowd of people, like let's say like people are trying to get into the exhibition and there's just a ginormous crowd of people. Apparently, people move in sine waves. So think about either if you're waiting in a long lineup or if you're in traffic. So when I'm in traffic, like a large traffic jam, you're standing there. Then you notice, oh, the cars are moving in front of you, so you slowly start. Then you get a bit faster, and then you slow down almost to a halt. And then you wait, and then you slowly go. You get some speed, and then you slow down. Like, no joke. Next time you're in a traffic jam, just notice how you're moving. It is modeling a sinusoidal wave. Or if you're in line for a concert or a theater, like, or a movie, just notice, is it sinusoidal? Are you sort of slowly moving, then speeding up, then slowing down to stop, and then repeating that motion? So sine waves happen in nature all the time. All right, there are other applications of sine waves. Now, here's the question. Is it possible to model each of the following situations using a periodic function? I'm not saying sine, cosine, just periodic, a repeating function. Seasonal variations in temperature over time. So averages, we're saying, i.e. the mid-season high temperature as recorded over 5-year period. So we're talking climate as opposed to weather. Remember from grade 10, climate. And we're not talking over thousands of years. We're just saying every year. Can we approximately call this a periodic function? Yeah. In the winter, it gets cold. In the summer, it gets hot. Blah, 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 blah. Right? We're talking averages. Yeah. So temperatures can be can be modeled using periodic functions, but we're going to say approximately. That's why we have to use averages. If I look at a weather curve, so here I do have a function of temperatures, okay, over a 2-year period, you do see that it does follow somewhat of a sinusoidal curve, right? Of course, not perfectly. Okay, let's look at sine waves. Do I have the next one? Yeah. Oh, guys, this makes me so excited. I'm such a physics teacher. Not that I haven't taught in 10 years, but I just love how physics has everything you learn in physics has a real world application. So here is what a sine wave looks like when we model it. Okay, a sound wave is not actually like you don't have particles going up and down and up and down. That's not how sound works. But how sound works is that we get these compressions of sound waves, of particles, and then rarefaction. So the particles spread apart. This is what I'm talking about, crowds and traffic. Okay, you kind of get, this is where you slow down, everything gets really tight, and then there's some room and you spread out, you get faster, you slow down almost to a halt. Okay, so sound waves work the same. So as I'm speaking, I am pushing particles in all directions and they go right into your ear. And then you have an eardrum that gets those pressures and then translates that into electrical signals that go into your brain. That's the other piece. Sorry, I'm going on a tangent. The other piece that I find fascinating is that our senses, touch, smell, taste, sound, they all rely on our brain translating electrical signals into senses. So it's not that our ear actually does the hearing. Our ear just receives the pressures, the pressure differences, and then sends electrical signals, and our amazing brain takes those electrical signals and says, "Oh, when I get this signal, that means Miss Sly is making this sound, this sound, this sound." Same with touch, same with seeing, smelling, right? Your nose doesn't smell, it just gets electrical signals. Your eyes do not actually do the seeing. Remember from optics last year? They don't actually do the seeing. They just get electrical signals, send it to your brain does the processing. All right. So sound waves, yes, they definitely model periodic sound. Okay, as you can see in that in the what's it called in the slide. All right, the next question is the amount of money in my bank account over time. Anyone's bank account have periodic behavior? Maybe if someone like lives paycheck to paycheck, right? So they get their money, they spend it, they've got nothing. They get their money, they spend it, they've got nothing. That could be periodic. Does anyone have a periodic bank account? Who does not have one? I don't. It's all over the place, right? Okay, so money in the bank account is not periodic because it would have to be very consistent. The height of a bouncing ball. So when you have a bouncing ball, let's say you're here, you start, it bounces. Does it go right to the same height? No, it doesn't. How come? Okay, it's losing momentum. What is it, Timur? Okay, I don't like the word loses energy. I guess the ball itself loses energy. What is it? It transfers energy into what type of energy? Thermal, sound. The potential is the potential can turn into kinetic, right? But every time your ball bounces and it makes a sound, that's sound energy that comes from the kinetic energy of your ball. There is actually some thermal energy, some thermal energy from the friction with the air, right? So a ball does not have periodic behavior because the height changes. So No. A pendulum on a clock. Okay, now this is assuming that there is extremely little friction, right? So a pendulum, if you have a pendulum with very little resistance, okay, and you just let it go, the great thing about pendulums is that they do have periodic behavior and in a sinusoidal way. Where do they go the slowest? At the ends or in the middle? Where do they go the fastest? Yeah. Can you use a sine curve for that? You could. Cool. All right. So you don't have to know that stuff. I just wanted to give you some examples of where periodic behavior happens in our daily lives. All right. I want you to read this question. Read it twice, underline it, underline what you're supposed to answer, underline the important information. Make notes. Yeah. All right, now that you've read it one more time to get all the details. All right, let's see what we know so far. So when I underlined the yellow, 1 full revolution in 48 seconds, what does that number help us find? Yeah, right? One cycle has a period of 48 seconds. So if I know, okay, so so if I know that my period is 48 seconds, what else can I find? We can find the K value. Okay, so the K value we find by dividing 360 degrees by the period. Sorry, my writing is not great today. So I get 360 degrees over 48 seconds. Is it 7.5?
Yeah.
Now, because it's a word problem, we need units. So what is it? What are the units? Degrees per second, right? If it's 360 degrees per 48 seconds, that means degrees per second. What does that even mean? We call this an angular velocity. So velocity is like a speed, and it tells us that every second the Ferris wheel rotates 7.5 seconds. So it's not moving horizontally, but it's rotating. So every second it's 7.5 degrees. Okay, it's telling you how quickly it's rotating. So this is called an angular velocity. Let's write that down. Let's put a star next to it. Okay. Okay, so we got that piece of information. We've got our K value. Hooray. Next, the radius of the wheel is 15 meters. So let's draw this Ferris wheel. I need a real circle. Okay, let's have you draw the whole situation. We've got a circle. Now, is the Ferris wheel flat on the ground? Okay. Let's say it's like on like a stand, right? So we need to find the middle. And let's say it's like got these legs that hold it up. And then we got the ground. Okay, so what do I know? I know this height. What is this height? 2 meters, because the Ferris wheel is 2 meters off the ground. I also know the radius, and that is 15 meters. Okay, let's look at that 15 meters. What part of the sine function or cosine function, what is it, Greg? It's the amplitude. So what it's saying is, from the middle of the Ferris wheel, the max height is 15 up, and the minimum height, the lowest height the Ferris wheel will ever have, is 15 meters lower from that middle point. So the amplitude, now which transformation is the amplitude? Yeah, the A value. It's our vertical stretch. So the amplitude A is 15. Okay, we can write 15 meters, but into the equation, we don't add units in the equation. Okay, what can I do with that 2 meters? I know it's something important. What is that thing called? Beautiful. Oh my God, you're so great. You're like all collaborating here. Right. So if this was the ground, my central axis would be right in the middle of the Ferris wheel. But because the Ferris wheel is raised by 2, it means that the central axis is 15 plus 2, i.e. the central axis is the location of the middle of the Ferris wheel. So central axis is at middle of Ferris wheel. Okay, and so that means, now which transformation is our central axis? C. So that means that C in this case is 15 plus 2, and that means C is 17 meters. Okay, we've got a lot of information so far. We haven't even started drawing this picture. And note that I like to find out all the information I can before I start drawing. Okay, is there anything else I need to find? Oh, what's the last thing what's the last transformation we could find? The phase shift. Now, we don't actually need the phase shift to start graphing. So let's start graphing. Before I start graphing, I like to personally graph the central axis and the max and the min. So the central axis, I'm going to make it red. The central axis is at 17 meters. Now let's check. 2, 4, 6, 8. Okay, this axis, the vertical axis, goes up by 2. So that means 17 meters is going to be right here. I would do it a dotted line, but I don't have that capacity on my computer. Right, so here's my central axis. That means the curve will always return to the central axis. Now my max is going to be at what height? That's right. What did you do in your head? 15 plus 15 plus 2. Good. Or 17 plus 2. Right? So the max is going to be 15 plus 15 plus 2. Right? That's 32 meters high. And what is going to be my min value? What's the bottom? What's the lowest point the Ferris wheel will ever reach? 2 meters. Okay, so I've got my min. I've got my max at 32. And so by drawing these lines, I know that my sine curve or cosine curve, whichever one, is going to oscillate between these lines, right? It won't go outside of these lines. The next thing I might want to mark is the period. So I know that this cycle repeats, the behavior behaves every 48 seconds, right? So let's just make a mark. Okay. At 0, at 48, at 96, 48 plus 96 is 144. So at those stars, that's the end of each cycle. Now, how many cycles are we supposed to draw? 3. So we have enough space. Okay, let's go. Where do we start? Where do the passengers sit down? What is it? The passenger gets on at the bottom and goes full 3 cycles. So we start at the minimum. Okay, I'm going to draw my lines. And now I know that we reach the minimum every 48 seconds. Remember, if the period repeats every 48 seconds, I know that my y value will be identical every 48 seconds. How long does it take for me to reach the maximum? Which is? Okay, cool. So at 24, I'm going to be at the max. Well, I'm going to be at the max 48 seconds later, which is 72. 48 seconds later, which is 120. Okay, I'm pretty good. How long at what point does it reach the central axis? Okay, so if it's from min to max, it takes 24 seconds. How long for the Ferris wheel to reach the central axis? It is a quarter of a period. So watch this. On our Ferris wheel, every quarter period is 15 seconds. Oh, sorry, not 15 seconds, is 12 seconds. Right? 1/4. Oh, that's not clear. 1/4 of a period. All right, so that means at 12 seconds, halfway through, we're at the central axis. And that happens every 24 seconds. This feels difficult. Okay, cosine or sine? Cosine, just a reflection, right? So let's draw a smooth curve, as smooth as you can. Okay, can I show you what not to do that I found on quite a few quizzes? I saw this. And yes, you do go through the dots, but that is not showing you a sine or cosine curve. It is periodic even, but that is not the curve. Okay, so you must attempt. Oh, bad. You might not have a steady hand like me. That's fine, but you're trying. Ah, man, that's really sad. Okay, I hope yours looks better than mine. Okay, so we have drawn. Let's write an equation. Okay, are we going to do that later? Write an equation. Oh yeah. Question B tells us to write an equation. Let's do that right on the graph as we're looking at it. Okay, so for the equation, What is the y-axis? It's not going to be y.
H.
Yes. Now, because we've been doing a course called functions, which we're going to write h of t. Okay, the t reminds us that this is the input and the height is the output. So h of t equals, what goes first? The a value. Oh yeah, what is our a value? 15. Now let's be really careful.
I think there may be a negative sign.
Oh dang, no, a negative. I think you're right. We do have to add a negative. And that is because we start at a minimum. Okay? So if you need to write that in, negative because we start at a minimum, you write that in. Okay? Now, we said it was a cosine curve. I'm going to use square brackets because we have a k value. Yeah. Yes. It would be like, the question is it wrong to write y? Communication-wise, absolutely. Because it's the incorrect variable. Yeah. So our k value, what did we find? 7.5. Instead of x, what do we write? T, that is our input. Okay. Now, do we have a phase shift? No, we had a vertical reflection. So actually, I don't need all these extra brackets. I can just write cos of 7.5 t. And then I do have a c value, right? A vertical shift. And we shifted up. So it's plus 17. That's my C, that's my K, that's my A. Could I have written this as a sine function? Yes, and if I did, what would be my phase shift? So where is the start of the sine function? Like right here. How much time has passed? 12 seconds. So it would not be wrong to write it as a sine function and give it a 12-second phase shift. Yeah. Because so the question is, why is the central axis at 17? The middle of the Ferris wheel represents the central axis. So we are told that the Ferris wheel is 2 meters off the ground, and the radius of the Ferris wheel is 15 meters. So you add these up. Does that make sense? Great, thank you. Yes, Mustafa?
For the I forget interval, like the time it takes to get to the central axis.
Yeah.
Wouldn't it be 7.5?
Oh, interesting. No, 7.5 is how many degrees it does in 1 second. So if you wanted to, you could say, okay, I know from the minimum to this point is 90 degrees. So you could say 90 degrees, 7.5 degrees per second. You could do some math to figure it out. You would get 12 seconds. Now, if we know, how did I know it was 12? One rotation is 48.
Oh, you divided by 4.
Yes, it is. The velocity is, the angular velocity is constant. So 1/4 is divided by 4. All right, so we have our equation. I'm just going to copy it down here. So I've got h of t equals negative 15 cos 7.5 t plus 17. All right. For how long in total is the rider at least 24.5 meters above ground? Okay, so in order to do that, we might need to do some math. All right. So what does 24.5 represent for us? That is the height. Okay, so this is the height. Okay, And this is where it gets a bit tricky. So we're going to take our equation. Okay. No, we're not going there. All right, we're not going to do this algebraically. All we're going to do is we're going to read from the graph. Okay, so it's important that you have a good graph, not like mine. So read from graph. So we go up to our graph and we're going to make a line at 24.5 meters. Now we know that that the Ferris wheel is above 24.5 3 times. So let's approximate. Okay, I've got 4 blocks. 1, 2, 3, 4, 5, 6. Okay, how many seconds does each block represent? Look at the time axis. Okay, if this is 24, every interval is 4 seconds. So I've got 1, 2, 3, 4. Do you have about 4? Okay, so I have approximately 4 intervals, which is 4 times 4 seconds, which is 16. Approximately, agreed? And that happens 3 times. So reading from graph, and we can say above 24.5 meters. Oh man, let me type this out. Above 24.5 meters for approximately 16 seconds each period, each cycle. And yeah,
You know that it's 16 seconds.
did you get something different as an approximation?
No, I'm just.
You're wondering. So question is, how did I know it was 16? So I drew a line at 24.5. And then I made an approximation. What is the distance? So the Ferris wheel is above 24.5 here to here. Okay, so I was like, how much time has elapsed? So, and I counted that I've got 4 units here. Now, each interval, each unit is 4 seconds. So it's an approximation. Okay, and so because each interval is 4 seconds, I estimated it to be 16 seconds. Does that make sense? Now there's 3 cycles, and so I'll multiply that by 3. So I go, whoa, I lost some. Okay. 16 seconds times 3, which will give me 48 seconds. I lost some words here. And so we can say, therefore, it is 24.5 meters above ground for approximately 48 seconds. Is there an exact way to do this? Absolutely. It takes us back to rotational geometry. Okay, it takes us back to the cast rule, and I don't need you to do that today, okay, or on the test. All right, let's look at another example. Go ahead and read it to yourself. Okay, so can we picture what's happening? Okay, there's a pier. So, like do we know what a pier is? It's like a jutting out, almost like a road that juts out into the water. Think of it as a wall. Okay, and the water starts off. Let's say this is the pier. This is the top of the pier. You can walk on the pier. The water at high tide is 1 meter below the pier. Okay? And at low tide, this again brings us back to grade 9 science. Isn't that so fun? At low tide, it is a full 5 meters below the pier. So what is the difference between high tide and low tide? How many meters? 4 meters. Which is what? Beautiful. It's not our full amplitude, right? All right. So as we're getting ready to draw this, I'm going to draw a line for my max. I'm going to draw a line for my min. Right? This is my max height. I'll call it H max. And I'll call this my min height, H min. Because it is, are we told that it's sinusoidal? No, we're not. But again, are we surprised that tides behave in a sinusoidal behavior? As such, we can model it using sinusoidal or cosine curves. So where is the central axis going to be? At -3, right in the middle. Okay. This is our central axis. I don't know why it's shaking. Okay. And now we need to know how often this cycle repeats. Okay. Over a period of 6 hours. Yeah. I literally found the middle. So the middle of -1 and -5 is -3. Okay. I could have also added them together. -1 plus -5 divided by 2 will give me that the C is -3. Now, where does the water start? It goes from okay, does it tell us that it starts at high? Yeah. All right, so we're starting off at high tide. How often will the water be at high tide? Every 6 hours. Good. So at 0, it's at high tide. At 6, it's at high tide. At 12, it's at high tide. 18. Okay, we could go forever, but we just need a few cycles. And then because this is cyclical, because it's a periodic and sine, it will be at low tide after how many hours? After 3 hours, in the middle of the period. So at 3, 9, yes. Liam?
In the question it says it takes 6 hours to go from 1 meter to -5.
Thank you. Miss Sly made a mistake. So from 1 meter to 5, it takes 6 hours. Got it. So that makes our period longer. Yes. So 1/2 of a cycle is 6 hours long. Okay. So what is our period in that case? A total of 12. And actually, that makes sense, right? If you think about the tides, every twice a day, you'll have high tides and low tides. All right. So at 12, we're back to high tide. At 18, we're back to low tide. And at 24, we're back to high tide, right? So 24 hours is 1 day. And so in 1 day, you will have 2 low tides and 2 high tides. And we can safely say that at 3-hour intervals or at 3, 9, we will hit the central axis, right? 3 hours after high tide, 3 hours after low tide, we hit the central axis. Okay, and now let's try to get a nice curve in there. Sorry about that. Is this, does this resemble a cosine curve or a sine curve? Yeah, and is there a vertical reflection? No, because it starts at a max. Great. So when we get ready to write our equation, we're like, okay, it's definitely going to be a cosine curve. Now we need to find some information. We need our A value, and that would be our amplitude. So how much higher is the maximum from the central axis? 2 meters, right? So our amplitude is 2 meters. We have C. All that is left to find is our K value. So K, we use the same formula, 360 degrees divided by the period, divided by 12 hours. And that gives us 30 degrees per hour. Now, this gets complicated to think about because the tides are not rotating. A Ferris wheel rotates. So giving it an angular velocity makes sense, right? It's like, of course, it's changing angles as it rotates. When we think about the tides, there are no angles to be measured, right? But the angle comes from us modeling the tides as a cosine function. So that's where the angular velocity comes in. It's going to help us find the height of the tide at a certain time. All right, so we'll write the equation. What will be our y variable? It's going to be a height again. Okay. Our amplitude is 2. We're using a cosine function. We have a K value of 30. Remember, you don't need to put units in here. The 1 unit I do like people adding, which quite a few people missed in the test, is I like you adding degrees for a phase shift, just to really say that this is degrees and not radians. What is our x variable? T for time. Good. Right? No phase shift because we're starting at the maximum. And then our central axis is -3. Okay? All right. Determine the tide level at 7 p.m. if low tide occurred at 8 in the morning on the same day. Okay, this is for the tide questions. This is where it gets tricky. So 8 in the morning is at time equals what? 8 a.m. at time equals 0. Oh, sorry. No, not time equals 0. Time equals what? 8 a.m. is low tide. So where is low tide? Low tide is here. What's time? Time equals 6 at low tide. Okay, so 8 a.m. is at time equals 6. Okay, so they're saying if low tide occurred at 8 in the morning, okay, so we know that this is 8 a.m. What is the height of the tide at 7 p.m.? So now let's look at how much time has elapsed. So between 8 a.m. and 7 p.m., how many hours would that be? Between 8 a.m. and 8 p.m., how many hours is that? 12. No, between 8 and 8, it's a full 12. So 1 hour less, 7 p.m., what are we saying? 11 hours, okay? So to find out what is the time at 7 p.m., it's going to be 6 plus 11. We get from 8 a.m. to 7 p.m. Okay, that's where we get the 11. And so that means we're looking for the height at time equals 17. So we're going to take this time and substitute it. That will be the input of our equation. So the height at 17 seconds, right, that's our input. And now we use the equation that we developed. 30 times 17 minus 3. So we take out our calculator. Make sure you're in degrees. Yeah.
Why did you add 6 and 11?
Okay. So at time equals 6, I have 8 a.m. 11 hours later, I get time, I get 7 p.m. Now, the x-axis is not the clock, it's the measurement of time. So you can't say, oh, 7 p.m., that's going to be 7 on the time axis. You actually have to see how much time has gone by since low tide. Okay? So pop this into your calculator. What do we get?
-4.73.
Does that make sense? -4.73 meters? What does that mean? Why do I have a negative answer? What is it, Lila? I didn't actually hear you. Say it again.
Like the minimum is already
Right. We are talking about a minimum height. Where is 0, folks? On our graph, where is 0? At the pier, right? And so the water is always below the pier level. And so when it's negative 4.73, well, at time equals 17, yep, I'd say that's a good approximation. Okay, so that means, therefore, the tide is 4.73 meters below the pier. Folks, you've got some homework. I'm really going to encourage you to do this homework because as you can see, this stuff is tricky, right? And luckily we get 2 days to review, but don't take that as a chance to do your homework. Like, bring your questions to me.